Have you ever thought about how the ukulele gets its beautiful sound? It turns out there's a lot more physics behind it than you would have thought. The sound is due to the frequencies coming off the waves of the string. My ukulele needs to be tuned to the standard C chord, which is 392, 262, 330, and 440 Hz, respectively, for each chord. The ukulele has 4 strings of equal length, which are fixed at either end, which makes it a standing wave. The pitch typically corresponds to the lowest resonant frequency, also known as the fundamental. Wavelength of the fundamental is equal to twice the wavelength of the string. Frequency is shown as equaling V over wavelength, therefore it cannot be shown as V over 2L. V is the velocity of the wave of the string. The equation to find all the frequencies is frequency equals N times V over 2L, where the N equals 1 to 3 refers to the harmonics. This equation can be used for all string instruments. Let me place my finger here on the string. What happens here is that the length of the vibrating string is now shortened. The frequency becomes higher now since the wavelength becomes shorter. Now that we have a basic understanding of the standing waves, have you wondered how each string has a different pitch when strung? This is because each string has a different mass per unit length, which has an impact on the velocity of the string. As we notice, one string will have a higher pitch than the other. Tension also plays a big factor in the frequencies of a ukulele. If it's not tuned correctly, this can cause a much different pitch. As I'm about to show here, you'll see how each string carries a different pitch. The tension can be controlled by the tuners at the top of the ukulele. As you can see, when I pluck the string, it's not the right pitch. So when I tighten it up a little bit, it's the right pitch now. The correct tension helps create the proper wavelength needed for the right frequency. You can see how frequency is influenced by tension by looking at this equation, V equals wavelength times frequency. Speed of the wave also equals V equals the square root of F over U, where U is the linear density of the string, U equals M over L, so putting this all together, V equals the square root of F over M over L. So what we can take away from that equation is that tension plays a very vital part in helping make the frequencies. So I can see these tuners are very important in making sure that your instrument plays properly and to the right sound. Let's do a practice example. Let's say my ukulele strings are 0.53 meters long and it's tuned to 300 Hz. What's the frequency of the sound wave produced, and what is the wavelength of the fundamental string vibration and sound wave? First, we can establish that the frequency of the sound wave will be 330 Hz, which is the same as what it was tuned to. The wavelength of the fundamental string vibration will be wavelength equals 2 times length. Using the values will be the wavelength equals 2 times 0.53, which is 1.06 meters. Wavelength equals V over F. Using the values is 343 over 330, which is 1.04. 343 represents the speed of sound. Overall, the ukulele is much more complex than you would have thought. Next time you're strumming your ukulele, or any string instrument in general, try and think about the physics that applies to it from what you learned from this. Thank you all for watching. Bye!